Hey everyone, and welcome to The Explainer. Today, we are looking right at the foundation of our modern world. Literally. You see, our built environment is currently undergoing this massive, sustainable engineering shift. We're going to explore how researchers and engineers are fundamentally rethinking the very materials that hold up our skyscrapers, our bridges, and our homes. They're taking what used to be massive environmental liabilities and transforming them into cutting-edge, green solutions. Okay, let's dive into this. 8%. That is the percentage of global CO2 emissions that comes from cement production alone. Honestly, it's a shocking figure. Traditional building materials like concrete, steel, and cement are just incredibly energy intensive. Their production relies heavily on mining, refining, and smelting. And that doesn't just deplete our natural resources, it pumps out a massive amount of greenhouse gases. The way we've been building our world is taking a huge toll on the planet. So making a change here isn't just a good idea, it is an absolute necessity. So here is our 5-step roadmap for understanding how we implement this massive shift. First, we'll look at the construction climate crisis. Second, the rise of green materials. Third, a fascinating case study on plastic concrete. Fourth, how we manage those environmental impacts. And fifth, we'll look at the future of construction. Let's kick things off with step 1. The construction climate crisis and traditional buildings' environmental toll. The contrast between these two is just absolutely stark. The old way, traditional construction, is completely defined by high energy inputs, heavy resource depletion, and a massive carbon footprint. We basically pull raw materials from the earth, use them once, and when a building is demolished, the whole shebang usually just ends up in a landfill. Conversely, green construction represents the new paradigm. It's totally focused on a circular economy, active waste reduction, and significantly lower emissions. It is all about designing materials that actively reduce energy consumption over a building's entire life cycle.
All right, moving to step 2, the rise of green materials and redefining how we build.
Let's ground ourselves in a really clear definition here. Green building materials are environmentally friendly alternatives specifically designed to reduce waste, lower energy consumption, and cut greenhouse gas emissions over a building's entire life cycle. Notice that word, life cycle. That's absolutely crucial. It's not just about how a material is manufactured, it's about how it performs while the building is actually occupied and what happens to it when that building is eventually torn down. And this brilliantly illustrates how we actually apply these things. We can divide the application of these materials into 2 types, structural and non-structural. Structural materials are the heavy lifters, your beams, columns, and foundations. Here, engineers are implementing things like fly ash-based concrete, recycled steel, and biocement, which replace carbon-heavy clinker with industrial byproducts. Then we have non-structural applications, which is essentially the skin and interior of the building. This includes your insulation, cladding, and flooring. For this, we're seeing incredible natural fibers like hemp and wool, as well as recycled plastic composites and cool roofing materials that reflect sunlight just to reduce a city's heat island effect. Let's get into step 3, our case study, plastic concrete and turning waste into foundations. Now, what's really interesting about this slide is seeing how everyday plastic waste can actually become a concrete aggregate through some highly distinct mechanical ingenuity. So, on one hand, defective preformed tubes, those little plastic blanks before they get blown into actual bottles, are crushed in a knife mill to create granular PET, or GPET. At the exact same time, post-consumer PET bottles are collected, washed, processed into flakes, and then heavily ground down through a process called micronization to create this fine, dark powder known as MPET. Both of these completely distinct recycled plastics are then used to entirely replace conventional sand and gravel in the concrete mix. Now, you might be wondering, why go through all that trouble? Well, let's contrast the two. Conventional quartzite aggregate, which is just the standard rocks and sand used in concrete, is incredibly heavy and requires highly resource-intensive mining. On the flip side, recycled PET aggregate takes a major environmental pollutant, plastic bottles, and repurposes it entirely. But the real engineering magic here is that the resulting concrete is actually categorized as lightweight structural concrete. It maintains the necessary compressive strength to actually build with while shedding a significant amount of weight. Let's look at the hard data. The specific gravity of standard reference mortar sits right at 2.00 grams per cubic centimeter. But that PET mortar mixture, it drops all the way down to 1.35 grams per cubic centimeter. That is an absolutely impressive 30% reduction in weight. And to put that into perspective, in civil engineering, a lighter building means you need less steel reinforcement, you can use a smaller foundation, and you burn significantly less fuel transporting all those precast materials to the construction site. But whenever you mix incredibly light materials like plastic and expanded clay into wet cement, you run into a potential problem: buoyancy. Will all the light stuff just float right to the top before the concrete dries and ruin its structural integrity? Well, to test this, researchers sectioned the concrete blocks and ran them through MATLAB image processing software. The analysis clearly showed that the dark squares, which represent the coarse aggregates, are distributed evenly across all sections, from top to bottom. They didn't just float to the top. So this proves the structural integrity and homogeneity of the mix are completely maintained. This brings us to step 4, managing environmental impacts and the circular economy in action. To figure out how this actually impacts the planet over time, engineers use something called a life cycle assessment. This basically means true sustainability isn't just about the day the material is made. It happens in 3 distinct phases. First is extraction and processing. Using recycled materials like PET means drastically lowering the initial energy input compared to mining fresh rock. Second is transportation and use. As we saw, lightweight materials save massive amounts of fuel during transport, and better insulation saves energy while the building is actually being lived in. And third is end of life. When the building finally comes down, materials should be designed to either biodegrade safely, like timber and bamboo, or be endlessly recycled, like steel and aluminum. So, the crucial point is that green building materials are really the engine of a true circular economy. By diverting waste, like our plastic bottles, away from landfills and incorporating them right into our infrastructure, we manage carbon emissions at literally every stage. We stop depleting our virgin natural resources, and we create a built environment that works in harmony with the planet, rather than just extracting from it. Finally, step 5, the future of construction, focusing on smart systems and bio-innovation. The next few decades of civil engineering are going to look like pure science fiction, and these innovations are coming fast. We're seeing nanotechnology being added to materials at the molecular level just to drastically increase tensile strength and durability. Bio-based materials are hitting the market, like using mycelium, which is the root structure of mushrooms, to actually grow lightweight, biodegradable insulation panels. There's even algae-based bioconcrete that literally sucks carbon dioxide out of the air while it cures. No way, right? We're also scaling up 3D printing and prefabrication to achieve zero-waste building sites. And my personal favorite, phase change materials, or PCMs. These are smart materials built right into walls that actually melt and solidify to absorb excess heat during the day and release it at night. They regulate a building's temperature passively, without any air conditioning. Let's move to and see how this builds into the real world, because these sci-fi materials aren't just staying in the lab. Government policies, subsidies, and strict green building certifications are actively driving them into reality. Frameworks like LEED, BREEAM, and the Green Pyramid rating system are giving developers massive financial and market incentives to use these sustainable materials. Hitting these certifications raises a building's market value and attracts investors, proving that going green isn't just ecologically necessary, it makes perfect economic sense. We have covered a massive shift today, from understanding the sheer scale of cement's carbon footprint all the way to seeing how a simple plastic bottle can be micronized, engineered, and turned into structural concrete. The built environment around us is evolving rapidly, so I'm going to leave you with this final thought. The next time you toss a plastic bottle into the recycling bin, ask yourself, could this be the foundation of your next home? Thanks for joining me on this explainer, and keep questioning how the world around you is built.